Hello, welcome to STAT MPH 701. This is the lecture one. It's from the chapter one of our textbook. I already posted the slides onto the canvas, and I hope this video will help you a little bit. Uh, because I wish you have already read the book and also the slides. And this video hopefully can help you to understand a little bit deeper about the essence of chapter one. There are five parts of this lecture. The first part is the introduction, which is not from the textbook actually. I added it myself. Hopefully, this introduction can give you a big picture about what this course, or more broadly, statistics or biostatistics is about. And the real start point actually is from the second one, the data basics. This and the rest of these four sections are strictly from the chapter one of the textbook. All right, let's start with the introduction. So I think the first question, for this kind of course is always tempting to ask what statistics is really about. And more strictly speaking, because our course is biostatistics, right? What is biostatistics? Oh, this is a good question. It depends on what kind of textbook we're going to use. Actually, here I picked two, I think my favorite, of course. Statistics is a discipline concerned with number one, organization and summarization of data, and two, the drawing of inference about the characteristic of some collection of persons or things when only a proportion of these characteristics are available for study. So, of course, this is kind of like a description of statistics, what statistics is doing. And for biostatistics, right, it's just that branch of statistics deal with primarily with the biological science and medical or health related disciplines. Of course, biostatistics is a branch of statistics. Statistics is really popular in many fields, right? Biostatistics is one of them. That's the way to understand. When we talk about statistics, the first pair we cannot ignore is population and sample. As for the definition of those two, actually is also very different. Okay, and here we could just say a population is a set of persons or objects having a common observable characteristic, which of course this characteristic is our interest. So, and here in statistics, population means not only people, but also what? Like the objects, things we are interested in. For more precise definition, we could say a popular population is a collection of persons or things in which we have a interest. For example, like collection of persons living in Florida who tested positive for hepatitis C, or the collection of deer in some county of Michigan that carries the tick responsible for Lyme disease might be this kind of examples. A statistical population is a collection of some characteristic of a set of persons or things in which we have an interest. You know, here statistical population emphasize the characteristic of among the other stuff, right? Which most of the time, I would say numerical facts. For example, like here, we could talking about the blood pressure of some set of students, right? Why we are interested in this kind of blood pressure? Because, of course, we say blood pressure is measured from persons, right? But yes, we are interested in persons, but more precisely, we are interested in the blood pressure of a group of persons or a particular person. Another example, like an indicator as whether each student has experienced some form of sexual abuse during her or his lifetime. So, from this kind of description, we can kind of get the point that, excuse me, statistics is kind of what is to deal with numbers, and those numbers could be understood as the numerical facts about the characteristic of the items, subjects, as well as persons, right? We are interested in. After we know what the population is, sample is very easy to define, you know, because if we think the population is that whole thing, then sample is just a part of it, right? Is a subset of population and maybe consist of persons or things or characteristics of persons or things depending on whether the sample is from a population or statistics population. Okay, so here the example say we may refer to a sample of 50 men over age 65 who suffered from hypertension, to a sample of 50 blood pressures taken on 50 men over age 55 who suffered from hypertension. So the population could be say any man age 65 or above, right? That's the population. But the sample is only what? We're only like randomly select 50 out of I don't know how many for how many age 65 or over men in the United States. That's a lot, right? So from this example, we could understand the sample, the relationship between the sample and the population. So sample is a subset of population. The second pair we want to talk about statistics other than population, the sample. We have to talk a lot is the data and the variable. So this word data, I would say, is abused a lot, right? So most of the time, if we're talking about data, kind of like is almost equivalent as sample. As we're talking about in the previous slides, sample is part of the population, subset of population. But in the real practice, what is sample? Sample actually is equivalent as data. For example, like we continue the example of the blood pressure. Yes. So if we randomly select 50 men age 65 or above, then we measure the blood pressure for each one of them, and then we have 50 numbers. those 50 numbers we can call it as data, as supposed to be sample. So I would say data is another real life word for sample. And in data, we have to talking about variable. What is the variable? Variable actually a characteristic which we are interested in is a variable, is a measurement. So a sample consists of 50 males. Gender is not a variable in this sample, but rather is termed as a constant. So what does this mean? Constant here, if we put these two words together, right, a variable and a constant is very easy to understand because a variable means the values vary. It's not just one variable. Like here, if we put a gender as a variable, we are supposed to have either male or female, right? But here, for a sample with only 50 males, then the gender is not this variable, really does not vary at all, right? Because it's always male. So basically says, I put these two terms here because I wanted to say, okay, variable is a characteristic, right? We are interested in is a measurement on the subject. And the outcomes of this measurement could be a value of constant. But most of the time, if this variable is a constant, we do not consider it as a real variable. So this is a very good indicator for us to check the data. If you get a data right, you found one variable, the values of the one variable is the same, then you gotta ask yourself, is it something wrong or not? Okay, okay. Now we have the third pair is the so-called parameter and the statistic. What is the parameter? Parameter is something we made it up for the population. For example, the average of the blood pressure that make up a population is calculated. The result is one example of a parameter. Here, we just say, we consider all the whole population of the United States, okay? So each has a blood pressure number. And then we add all, I think, over 0.3 billion numbers together and then divided by how many, the total population, right? That's what we mean by the average of the blood pressure. So this average blood pressure is a parameter. We know this parameter is to describe the blood pressure of the whole population. And as we know, this number is really hard. We can say even impossible to get, right? Because it's really, really hard. As we know for the census, right? The census is the highest level of the highest level of this kind of or most precise numerical facts about the United States. It can only be done like once every 10 years. So it costs a lot of money and time. So that's what we mean by parameter. And Since the parameter is our interest and is so hard to get, that's why we come up with the idea the population is nice, right? Is out there, but it's hard to get. What we can achieve, what we can do in the real life is what? Is what we can get as sample, right? As data. And a statistic exactly is any summarization of the elements of a sample, a data set. So parameter is for the population. Statistic is for sample. If uh, if we want to use one line to describe the relationship between those two terms. Now we could summarize in a picture here. So the first pair we're talking about is the population and the sample. Population and sample. We know sample is part of the population. So sample is out of the population, right, by the sampling process. According to this parallel, we have parameter and the statistic. We use the parameter to describe the population. We use statistic to describe the sample. And then how can we go from statistics to parameters? This process is called inference, right? That's exactly the essence of statistic. We want to know something about the population. How can we do that? Yes, we want to know the population. What do you want to know about the population? We want to know the parameter of the population, right? The parameter are the concrete targets of our interest. And how can we do that? Okay, we take a part of the population as the sample, and then we use sample statistics to describe it, right? Based on that, we can say something about the parameter. Later, we were going to learn the first example of the population parameter and the sample statistic is the so-called population mean and the sample mean. So the population mean is a parameter for the population. Sample mean is a statistic out of the sample. And then statistic is what? Is based on the sample mean statistic, we would say something about the population mean, the parameter. I hope this section will give you at least a big picture about what statistics, or more precisely biostatistics, is talking about, is doing. Okay, under this kind of big picture, our starting point in this course is what? Is right here, the sample, okay? Because for this sampling one process is not in our course, because in statistics we have a course is called sampling. The whole course is talking about how to deal with connecting data, okay? Our starting point in this course is we have the data set already, right? We'll say something about the data first, and then our focus is really this part, okay? Describe how we're going to use the sample statistic to describe the sample. Basically say how we're going to summarize the data. And also the second step, based on the statistic or statistics, how we're going to infer about the population parameters. Okay, 2 jobs in this course. So next we're going to start with the so-called data basics, right? Because as I said just now, sample is the starting point of our course, right? Sample has a different name as data. That's why we're going to start with the so-called data basics. And the textbook started with a very real life case study. Okay, so please read that part. So as I I want to simplify as what as this one, right? We're talking about a little bit of R. Now you understand what this means. Hopefully, you have the library. That's the package. OI biostat package ready, and then use this data word. We can just import the data into R, and then we will get a summarized table like this. So now we say this table as here to put as a so-called data matrix, right? This is a data set, okay? This is a data set. In this data set, we have each column as what? As a variable, okay? Sex, age, race, height, weight, and then these two complicated, I even do not bother to plans, okay? So, all right. Let's talk about the variable. For the variable, most of the time, for data set, right? Data set is composed by each of those variables. For each variable, most of the time they have a name. Of course, this is a very concise. Most of the time, is not that long, short, kind of short names. And in the dictionary, they usually have a longer description about what this variable is about. For example, like sex, right? This is about the sex of the participant. Age, like age in years. Okay, sometimes age could be in months, right? Because if we are interested in babies, because for the newborn babies, I think their age could be years, days. And height, for example, like United States, height in inches, right? Like weight in pounds. Okay, so this is the kind of the routine in the practice. Okay, so data set, right? Usually they are accompanied by a data dictionary, which describe the names of the variables, details of the variables. Okay. Now, after we know what a data set, what the variables are about, now we're gonna go a little bit deeper. Okay, pin down to types of the variables, because definitely variables are definitely the workhorses we're gonna work a lot later in this course. So we have to get a little bit deeper about the variables. Among all the variables, we are dealing with two types. The first one is so-called numerical ones, numerical variables. Okay. So numerical variables take on numerical values such as what? The blood pressure, right? We're talking about it just now. Weight, height, right? So they are values, real meaningful values. As here we say, they are reasonable values, right? Okay. And there are two kinds of numerical values. The first one is so-called discrete. For example, like numbers of family members, right? We have, so this is most of the time we mean by count values, count variables. So they take integer values, right? Here. But in real life, numbers are not always integers, right? So we have so-called continuous values, which means we can take any value within a specific range. For example, like a height. We say somebody is 7 feet 3 inches, right? Like income, dollars, like hours, like for time. So most values, numerical values in real life are continuous. For other than the numerical values, we have categorical variables. Categorical variables, uh, they take values, right? They could be numbers also, but those numbers are not reasonable, are, are not meaningful. They are not real numbers. For example, like we say uh, the the best example I use here is always say end of the semester. You guys are gonna evaluate my teaching, right? You're gonna ask either my teaching is good, not that good, or very, very bad. These kind of categories, right? So we could use, for example, like one as no. Let's use smaller numbers or bigger numbers. Okay, so here we say 3 means good, 2 means not that good, 1 means really bad. Okay, so 1, 2, 3, 3, 2, 1. Okay, those are 3 numbers. But we know here those numbers are what? Are 3 categories. Of course, those 3 categories they have order, right? You know, 3 means good is better than 2, not that good. But and for 2 is better than 1 because not that good is better than bad. So this is for the categorical variables. We also have 2 categories. The first one is ordinal, as the example I raised just now. There's another one is called nominal. They're just pure categories. For example, like gender, male or female. There is no order, right? Also, like the weather, right? Is raining, is sunny, is cloudy. Like a color, red, green, blue. So they are just categories. We do not have any order among these categories. That's what we mean by categorical variables. Now we can summarize the types of the variables as this picture here. All the variables can be decomposed as numerical and categorical variables. Each has 2 subcategories further. For numerical, it could be discrete or continuous. For categorical, it could be ordinal or nominal. Now, given a variable, we should know whether it is numerical or categorical, right? If it's numerical, you need to tell is discrete or continuous. If it's categorical, is ordinal or nominal. You are supposed to do that after this. After we finish the types of the variable, and then we have to talking about how to deal with those variables, right? As we said just now, variables are our workhorse. How to work with those workhorses. And we have kind of 2 tools. One is called numerical tool, or we can say summarize data in the numerical way. The second one is graphical tool to summarize the variables in a graph or graphs. Let's talk about numerical variables first. So we have a bunch of numbers, right? For example, like the blood pressures, we have many, many numbers. And if we are facing a lot of numbers, right? What would be the best way to describe, to summarize those numbers? The first characteristic we're interested in is so-called center, right? Center here means we have many, many numbers, right? You could understand the center as what would be a very good representative for those many, many numbers? And in the practice, in statistics, we have two tools for that. One is the mean, the other one is the median. And after we picked a representative for many, many numbers, we have to consider, we still have to pay a little bit attention to the individuals, right? For the individual observations. And we want to know how this representative deviates from each of the individual. That's what we mean by spread. How similar or varied are the values to each other, right? Compare with that center, compare with that representative. First, we talk about the measure of the center is the mean. Sample mean, uh, if definitely is number one choice, okay? It's very straightforward. If we have many, many numbers, right? For example, like here we have n numbers, x1, x2, xn. How can we get the mean? We add these n numbers together and divide it by n. That's it. Back to the example, the farm mass example we have in the textbook. We wanted to know the average weight for yes, for how many people in the data set. That's a good question. Okay, you go back because you already have your R ready, right? Go back, check. But in R, actually, to get the mean is very easy, right? You just use this function mean to get the average as 155.6479 pounds. Okay, so it's about 166 pounds. That's the average. What do we mean by the center? Now you have this one, right? This is kind of the average. And then just pretend you are one of the individuals in the data set. Then you can compare your weight with what? This 156. Other than the mean, there is another measure for the center. It's called median. Median is real value of middle observation, the center, right? The center in the location. So how to figure out the median? That depends on the number of observations. If it's odd, if the number of observation is odd, we have a what? Middle, right? Because for example, 5 observations, and the third one is the middle, right? But what if the even? So if it's an even number, the median, we could not find a observation which is in the middle. With that regard, we have to what? Average the middle 2 observations as the median. This is the way to figure out the median. But nowadays, right, in the R, we just use the function median to do it, okay? It's very straightforward. So this is kind of the variable of the weight on the data set, right? You can see here. And how we can let the R know the variable. So this farm mass is the name of the data set, right? With the dollar sign, weight is the variable name, okay? Please learn this trick in R, okay? After we know the center of the data set of a variable, how are we going to figure out how the rest values of the variable vary from the center? That's what we mean by spread. Spread, we have 2 ways to measure it, okay? The first one is the so-called sample variance. Sample variance, the idea is very straightforward, right? We have the center as the mean, x bar. Now we subtract the mean from each of the observations, x1, x2, up to xm. We square this deviation, add them together, and then divide it by m minus 1. Okay, two questions here. Number one, some of you may say, why do we need to square this deviation? Just ask yourself, if we do not square those deviations, we just add x1 minus x bar plus x2 minus x bar plus xm minus x bar, what do you get? You will get a 0. Okay, think about why. So basically say, if we do not square those deviations, no matter what kind of data set you have, this top is always 0. Okay, that's a problem, right? That's why we need to square it. Second, why do we need to divide it by n minus 1 instead of n? Because on the top we have how many terms? N terms, right? 1, 2, up to n. But why we divide by n minus 1? In statistics, this is called lose 1 degrees of freedom. What do we mean by that? That's related to the first question, because if we add those unsquared deviations together, we get a 0. That means if we have n numbers, we know the sum of those n numbers is 0. As long as we know n minus 1 numbers, the last number is a fixed number. Basically say the last number does not have any degree of freedom at all, right? As long as you know the first n minus 1 numbers, the nth number is what? It is a fixed number. That's what we mean by lose 1 degrees of freedom. That's why we divide by n minus 1 instead of n. Okay, after we get the variance, sample variance, we take a square root of that. That's what we get a standard deviation. Of course, why do we need to take the square root? Because it's also for the practice purpose. For example, like the height, right? We measure it in inch. So you square it, right? Then the unit will be inch square. What does inch square mean in the real life? That means the area, right? Because remember, right? Because that's the measurement for the what? For the area. For example, like the area of a rectangle, we use the height times the width. We get inch squares. But for the height, this inch square does not make any sense. But after we take a square root of the variance, then inch squares will become inch. That makes perfect sense. So in the real life, in the real practice, standard deviation is more popular than variance. Of course, they are equivalent, right? Because bigger variance, of course, have a bigger standard deviation. But standard deviation is more practical because the units. Okay, second measurement of the spread is so-called percentile or quantile. So the percentile is the observation, just one observation, okay? Such that among all the observations, either from the lowest one to the largest one, right? Most of the time we go from this order, okay? From the smallest one to the largest one. And then there are p% of them are falling below this observation. For example, like 25th percentile means what? If we have 100 observations, right? Then we could find a number which is among these 100 observations, we have 25 are smaller than that one. So since this 25th percentile is so special, 25 is like 1/4 of 100, right? We just call it as the first quartile. We simplify as Q1. Then we have the 50th percentile. 50th percentile, that's equivalent to median, right? That means if we have 100 observations, we have 50 numbers are smaller than that median, and the 50 numbers are bigger than the median. So the median is kind of like what? Like split this whole 100 numbers into two halves. That's the idea. So median is also simplified as Q2 because it's the second quartile. And then 75th percentile is called simplified as Q3. Based on the quartiles, we have defined this so-called interquartile range, IQR, as the difference between Q3 and Q1. Okay. So, yes, we could use this individual percentiles, right? Q1, Q2, Q3, or whatever the percentile you could come up with. But here, IQR is more popular to describe the spread because you can see here we could use the R command, SD as standard deviation for the same variable weight, right? And also IQR for the IQR of the weight variable. Okay, the last example I really want to raise here is percentiles actually are very popular in our daily life. For example, if you take a test, right, other than a grade, specific grade, for example, like 80 out of 100, you'll get a percentage after that. The percentage, for example, like 80%. What does that mean? I think this one is more meaningful to tell you your standing among a group of people, right? For example, 80%, what does that mean? That means you're kind of the 80th percentile. Your grade is the 80th percentile of all the grades available in that pool. Okay, does it make sense? So, for example, if we have like 100 people, right? A group of 100 people, your percentile is like 90%. What does that mean? Your grade, there are 90 people who get a grade lower than yours. It's very popular in the real life. Now we're talking about a little bit. So what do we mean by robust estimates? Robust estimates basically says they are less likely to be affected by extreme values. What do I mean by that? We can raise a very simple example here. See, we say mean this measurement is not robust because it is very sensitive to the extreme values. Here is a joke, right? Think about I use this example a lot in the classroom. I once joked around to say, if Elon Musk entered in our classroom, then everybody here is gonna be billionaire. What does that mean? Because if we think of the mean wealth of a group of people, right? For example, like 20 students in the classroom, and then with the Elon Musk enter the classroom, and he is what? The richest person in the world now, I guess. And then because his wealth is still huge, right? We add his wealth in and then divided by For example, 20 now becomes 21. So the average definitely is a huge number. Think about these two means, right? With 20 people and with 21 people with Elon Musk in it. The mean for these two scenarios are so different. Is that correct? That's what we mean by mean is not robust estimate. But think about the median, you know, with Elon Musk or without Elon Musk. The median wealth of the 20 people or with Elon Musk 21 people does not change that much. The same thing can be observed among the standard deviation and IQR because we know both to describe the what? The spread, right? And IQR is robust, but standard deviation is not. Other than those numerical summarizations for the numerical variables, right? We could use a chart to describe numerical variables. For example, like for this weight variable, we can use the histogram. So histogram just make bars of the values between those ranges, right? So we have higher bars and lower bars. What does that mean? That means those kind of weights, most of them are around what? 140. Kind of from 140, 130, 140, 150, around this group, right? We observed, of course, some extreme values over 250s, right? And also we have some less than 100 pounds. But most of them are around these two bars. And the overall shape is kind of like what? You know, for this overall shape, we could have a like a curve among the top of that, right? Yes, it's not symmetric. It's kind of, you know, skewed to the right. That's the overall shape. So that's how this histogram can tell us, right? Because it can give us, tell what we know about the center. Here's kind of the center, right? Because most weights are around these two bars. And also tell us the overall shape is like a skew to the right. This is a histogram. So histograms show important features of those of the shape of a distribution, symmetry or lack of it, right? That's what I mean by skew. Like the previous picture is skewed to the right. Tell us the minimum and the maximum values. You know, minimum and maximum values, because you can see from here, minimum could be 90 and the maximum could be 400. Okay, at least give us a range, right? You know, about the minimum and the maximum. And the regions of high frequencies, that's what I mean by mode, like these two bars. Histogram not good for what? Displaying the median and the quartiles, this kind of spread for the center or the spread, right? And show more precisely about the skewness or extreme values. What we can do that, we can just use the so-called a box plot. So the box plot is a box right here in the middle. This is the box. So this top line of the box is the Q3. Okay. Check what Q3 means here. Okay. And the bottom line is the Q1. And the middle one is the median, right? Basically Q1, Q2, Q3. And then other than this box, we have two whiskers, the upper whisker and the lower whisker. And sometimes we could find some values beyond the upper whisker or below the lower whisker. Those are called outliers. Okay, yes. That's how the box plot is defined. Yes, we should pay special attention to those outliers. How the outliers are defined, because whenever this value, large outliers, right, means the values are big, then go first of all is go over Q3, right? Because Q3 is here, is way over Q3. So the distance between Q3 and this upper whisker is the what? 1.5 times the IQR, interquartile range. What is the interquartile range? Basically the length of this box, right? The height of this box from Q3 to Q1, this one. Then that's a larger outlier. Small outlier is, we're talking about the other end, is the Q1 minus 1.2 times the IQR. What does that mean? Yes, we could have like go below this one, okay? Because this is 1.5 IQR and even smaller than Q1 minus this one. That's below this lower whisker. That's a lot smaller outlier. On the box, you can see here, the rectangle extends from the first quartile to the third quartile. The rectangle is what we mean by box. With a line at the second quartile, the median. Whiskers captures the data between these two ranges, right? Potential also with the dots, okay? So we just use dots to show those are what? Outliers. So compare with histogram, box plot is more precise than histogram. What about the categorical data? For the categorical data, because they are categories, right? So we are talking about a so-called frequency table or one-way frequency table here. What is frequency table? For example, we're talking about this type of genes, right? We have three types: CC, CT, TT. So we just list how many observations for CC, how many observations for CT, how many observations for TT. Basically, how many CCs, how many CTs, how many TTs, and then we summarize it. So in R, it's very easy to do to use the command, use the function table, and then this is the variable. This is the name of what? The data. This is the name of the variable, and then this is the function. Okay. And other than the table, right, frequency table, one-way frequency table, we could use also a chart. For example, here is the bar plot. Bar plot, basically, we put 3 bars, basically means 3 categories, right? And the height of the bar is what? Is the frequencies of that category. So here, after this chart, you clearly know that the CT is the what? Is the mode. Is the most frequently observed category. All right. After we know how to describe a single variable, then the next question, also the last topic for this lecture, is how to investigate the relationship between 2 variables. Here we have 3 categories: 2 numerical variables, 2 categorical variables, 1 numerical and 1 categorical variables. First 2 variables are numericals, and then we are more interested in other than the single one, right? Because they are center, they are spread. We are more interested in the relationship. What do we mean by relationship? Relationship is what is the response for y corresponds to the change of x. So there are two scenarios, right? If x increases, y either increases also or what? Decreases. For example, like for the height and weight, uh, generally speaking, we know these two are what? Positively associated, right? What do we mean by positively associated? Because usually a taller person will have a bigger weight, okay? Right? And this relationship can be depicted in a picture here. For example, we put the x as the horizontal variable, okay? X variable as the so-called what? And the y is the weight variable. And then for each of these dots corresponding to a height and a weight, right? And then we plot many these height weight pairs into a system. That's how we get so many dots. And then we got these dots from this. This is called a scatter plot, okay? Yes, in R, that's how we do it. And then we can eyeball a line, okay? You can see this line. Yes, this line is kind of what? Is upward sloped, right? So it's positive. That means the height and the weight, the overall relationship between the height and the weight is positive. Or equivalent to say weight is positively related to height. But usually we do not say the other way around, okay? We do not say height is positively related to weight, okay? That's why we put the weight as the y. Other than the chart, right, to describe the relationship between two numerical variables, we could use a numerical way to do it. That's why we're talking about the correlation coefficient. That's correlation. How to get the correlation? It's very easy in R. We just use COR, right, and then put the two variables, height and weight there. But in the general definition, this is a number, take the values between -1 and 1. Closer the R is to -1 or +1, that means the stronger the linear association. What does it mean? Because we know this is between -1 and 1, right? And we know the center is what? Is 0. So if this R, yes, usually we use R or little r to denote, okay, is very close to either the -1 or +1. That means what? This linear relationship is very strong. But if it's very close to 0, then it's not that strong. For example, like the height and weight, we get a 0.5 something. Yes, it's kind of like a median, right? Median strong, okay? Okay. And so this R can give us two information. Number one, whether it's positive or negative. That tells us the relationship is either positive or negative, okay? So that's kind of the direction, right? Second, whether it's close to 1 or -1 or close to 0, or you can say the absolute value of this correlation is close to 0 or close to 1. If it's very close to 0, that means the strength of the linear relationship is not that strong. If it's close to 1, that means the strength of the relationship is very strong. Of course, if you get 1, that's the strongest, right? Think about this question. What kind of numerical variables the correlation is 1, okay? Think about it after class. How about the two categorical variables? For two categorical variables, we have used so-called contingency table to summarize. What do we mean by contingency table? Because if we wanted to know the race, right, and the genotype, okay, how can we do that? We just put the race, they have like 5 categories. Genotype, they have 3. And then we put it as row and column. They split as what? As this many cells, right? Because here, for example, African, how many of them have the CC type? 16. Asian, 21. Caucasian, 125. We just list those observations like that. That's what we mean by contingency table. In the R, we can just use this this guy, this function to do it, right? Because yes, table. Yes, they put this proportion because they just want to use the proportion, use the decimals. Okay. At the margins, they just add those names of the categories. Okay, these ones. We can also use the charts to describe the relationship of the two categorical variables, right? For example, like here, we use 3 types of the genes, right? CC, CT, and TT. And then in these bars, we put it in different colors. Different color means different race. You can see here, African, American, African, Asian, Caucasian, Hispanic, and other, right? And from this chart, we clearly know among these 3 types of genes, most of them have the CT, the type CT, okay? And among each type, which one has the largest part, okay, is the blue, right? Blue means Caucasian. So use this kind of tools to describe the relationship of these two categories. And as a numerical measurement for the relationship of two categorical variables, we are going to use so-called relative risk to measure this the relationship. Okay, so we just mentioned this term here. As for the details, we're gonna talk about in later, because we're gonna use a very specific example to describe it. Hopefully next week, okay, or the week after the next. And how about just one numerical and one categorical? Okay, for example, like this case, right? The gene type, right? And these numerical variables. What is the last variable? Yes, these are numerical variables. Okay, for 3 types, right? We observed those numerical values. Then basically say we have 3. We just do each category as a what? Box plot, right? All right. In the end, what we have learned. So I would like you at least have 3 takeaways. First, you should have a big picture about what statistic is, okay? Big picture of what statistic is, right? And that beautiful picture we have in the slide, at least You need to know that. The second, in the real life, right, we are talking about so-called data. We need to know some basics of data. First, you need to know what data is, right? And then third one, which is the most important for us, right? We're talking about the variables because data is composed by variables. That's why we're talking about the types of the variables. We're talking about how to describe variables, right? And then if we have two variables, how we're gonna describe the relationship between these two variables. These two variables could be two numerical variables, could be two categorical variables, could be one numerical and one categorical variable. And as we know, we have two ways to do it, right? Either by numerical, just use numbers, or by graph, by charts, right? So it's a lot of work, and thanks for watching this video, and please read the textbook also for details. And if you have questions, please email me. Let me know. See you next time.